Hello, everybody. Hello, Internet. Welcome again to another Bay Area Rust meetup. We got a great lineup tonight. Very glad you're all here. So, right there okay, figured it out. All right, first off, thanks Mozilla once again for feeding us and giving us a wonderful place to host these and loaning us their AV people in order to film us. It has always and will always be awesome. You guys are great. All right, so our agenda tonight, we have a variety of things going on. We're going to open the night talking about a machine learning library called ResMachine. Then we change gears a lot and start talking about an embedded operating system talk. And finally, over the internet, we're going to be talking about a Rust bioinformatics project. So anyway, the other thing that I wanted to mention before we start is that we actually have a lot of things coming up. We're getting to be conference season. RustConf is in early September, and I believe the registration closes on Monday. So if you want a ticket, you should buy one out. No.
They're open until we sell out.
All right, they're open until we sell out.
It might be the
But-
scholarships might be closing. Maybe
Oh, oh.
The tickets are definitely open until we sell out.
All right, Steve says scholarships might be closing soon. So if you want a scholarship, you should.
That's true.
It may or may not be true. We might be tricking you into buying. You know, supplies are selling out quickly, so buy now. Likewise, all the way over in Berlin, Rust Fest will be happening mid-September. I don't know about their tickets. I'm sure they're selling out, so you should buy them too. And finally, in October, we have the Rust Belt in Pittsburgh. And I also forgot that the next event that we have here is a kind of a different fair. It's a workshop-a-thon. The Rust community team has started building workshops as part of our Rust Bridge event. So if you want to help build content for people who are new to Rust or people who are new to programming, it would be really helpful if you came on August 13th. I can read. August 13th and help build workshops and stuff. All right, so that's it for me. And so now on to James. Whoops, wrong way. All right, James, take it away.
I think it's the wrong slide here as well.
Was that?
This,
Oh, there we go.
and, is the screen still split, Eric?
It is not split. You can see it right there.
Okay.
Do you want
I had some slide notes, but if you can't get them up, it's fine.
I can very quickly.
Sorry, everyone.
Let's see, will that? We can get this to work.
I think it's one more over.
Well, yeah, but I'm not sure how to move.
We can go without them if we need to.
Do you know? Wait. We can do this.
So
Technology. There we go. I'm not sure how to make this full screen.
I can help that then.
Okay.
Hopefully. So. Okay. Sorry about that. So thank you for the introduction. I am James. I'm going to be talking to you about RustyMachine, which is a machine learning library written entirely in Rust. So a quick disclaimer, I'm a mathematician by training, so I'm sorry if it's a bit math heavy in places, but please interrupt me if I'm not explaining things well. Feel free to shout out at me and tell me to go slower, go quicker, whatever. Okay, so in this talk, I'm going to sort of briefly go over what is machine learning, sort of try and introduce some basic concepts that sort of motivate RustyMachine. And then sort of talk through a little bit about how RustyMachine works, how it makes use of Rust, and then finally try and convince you why RustyMachine is great, or maybe more generally why Rust is really good for machine learning. Okay, so what is RustyMachine? As I said, RustyMachine is a machine learning library that's written entirely in Rust. So by entirely, I mean that it has sort of no external dependencies on common libraries like BLAS and LAPACK, which you sort of generally see for this machine learning space. Sort of the motivation behind that is that I wanted a machine learning library that just sort of works out the box. And Rust provides a nice place to do that without sort of sacrificing performance. So it focuses on the following things: works out of the box without relying on any external dependencies. It has a simple and easy to understand API that's sort of motivated by some other sort of longer standing machine learning libraries. And it tries to be extendable and easy to configure as well. So a really common question is, another machine learning library, really. There's like hundreds in lots of different languages. I just want to say that Rusty Machine is more than deep learning, which seems like a pretty valid thing to say today. A deep learning sort of seems to take up this big space in machine learning, but there is still, a lot of use cases come from places other than deep learning, and Rusty Machine sort of has a focus on that space. And the other thing is that Rust just seems like a really good choice for machine learning. As I'll try and sort of convince you as we go forwards, it has a lot to offer. And I thought that it would be really rewarding to sort of explore what this looks like. And it ended up being very, very rewarding. Okay, so on to sort of machine learning. What is machine learning? So I really like this quote from Arthur Samuel, which says that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. And how do machines learn? Hopefully I'll explain a bit more as we go forward, but the key point is with data. So let's sort of look at some examples to try and solidify what machine learning is. So one example of machine learning could be trying to predict your rent increase. So let's imagine that you're currently living somewhere in San Francisco and you want to figure out how much your landlord's going to be trying to get you to pay in a couple months' time. So machine learning can be used to sort of help us solve this problem. And the process we'd go through to solve this would be, first of all, we need to gather some data. So you can imagine that we might gather some rent prices from Craigslist and a bunch of other facts about the residents from sort of various government ordinances or anywhere else you can get your hands on it. We then use this data to train a machine learning model, and then hopefully we could then gather the same facts about our own residents to predict what the rent increase will be for our own place of residence. Another example could be predicting whether an image contains a cat or a dog. Not a particularly useful example, but in this case, the idea is that we're sort of feeding our machine an image that has like an animal in it, and we don't tell it what the animal is, and we want the machine to tell us this is a cat or it's a dog. So in order to do this, we have to train the model with some data which is made up of labeled pictures of cats and dogs. So first we sort of teach the machine what a cat and a dog looks like. So show it a picture of a cat and say, this is a cat. Show it a picture of a dog and say, this is a dog. And then hopefully after some time, we can show it a picture without saying what it is, and it tells us. So I mean, as I said, this is a pretty mundane, silly example, but you can imagine that maybe this is used in something like automated driving, where we need to detect whether an image coming from a camera on the car is of a sign or not of a sign, or something similar. And another really common example that you sort of see thrown around a lot in the sort of machine learning space is understanding handwritten digits. So in this case, our data set would be lots of examples of handwritten digits where we label them and say, this is the 0, this is the 1, this is the 2. And then the challenge for the machine learning model would be to show it one of these digits that's been drawn fresh without a label and have it tell us which number that digit belongs to. Okay, so I've used sort of some terminology there. I'm going to sort of go through it step by step and explain what that stuff means, because it'll be useful as we go forwards. So first, a model. I'll use this as an example after to try and make it clear what they are. But and these aren't really official definitions so much as the way I'm describing them to help with the talk. So a model I'm sort of describing as an object that transforms inputs into outputs based on information in some data. And we use training or fitting a model is the act of teaching the model how it should transform those inputs using the data. And finally, predicting is now feeding in new inputs to the model to receive the outputs. So to go back to sort of one of our previous examples, when we're predicting rent, we might use a linear regression model. That's a type of machine learning model. We train the model on some existing rent prices and facts about the residences, and then the final step of the flow would be predicting the rent of unlisted places that we don't have the price for currently. Okay. So why is machine learning hard? Obviously, machine learning is inherently difficult, so I'm not sort of trying to say that there's some key points that make it difficult. But I think on top of the sort of standard parts is the fact that there are many, many models to choose from. So when we're solving this sort of rent problem, there's an infinite space of models that we could choose. And on top of that, there's many different ways to use each model. So a lot of sort of being a machine learning engineer or data scientist is finding the right model to use, and then once you've found that model, trying to tweak it in all the various different ways you can to get sort of a model that fits the data well. Okay, that's all I'm going to say about machine learning for now. Maybe we'll sort of go back and talk about some other things as we go through. But now I'm going to start talking about Rusty Machine and sort of how it solves some of these problems that I've described in the machine learning space. So the foundation of Rusty Machine is this, what we call a trait here. So for those of you that aren't sort of that familiar with Rust, a trait is sort of like an interface in another language. It's a set of functions which the implementer should define. So in Rusty Machine, we use this trait model to represent a machine learning model, as we discussed before. And the model has sort of two key functions it has to implement. The first one is train. So train in this case is transforming the model to understand, to teach it how it should transform the inputs into the outputs. And predicting, which is now giving it a new set of inputs and asking it what the output should be. So we sort of can capture this sort of key flow of a model using this trait. This is a little simplified from the actual traits used in Rusty Machine, but for sake of illustration, I've kept it as this. Okay, so it's been sort of very theoretical and explaining a lot of stuff right now, so I'm going to jump into an actual example of using Rusty Machine. So this example will show how we use those functions from the model trait to do some machine learning. So I'm going to be talking about a k-means clustering model. So k-means is the type of machine learning model that's used for the problem of clustering. So clustering is a machine learning task where we want to group together items that are similar to each other. So similar could mean they're close together in space, they share similar features in some other way. So in the sort of plot I've got here, you can see that there's lots of different points in 2D space, and you sort of roughly make out there's sort of two sort of origins to these points, sort of two balls of points that are concentrated. So the idea is that we could use k-means to try and to try and classify which point each ball belongs to. So this is what using a k-means model looks like in Rusty Machine. So there's sort of three lines that make this up. The first is we create the model, so we have the let mut model equals k-means classifier new, and we specify that it should have two clusters. So with the k-means model, we have to say how many clusters it will have explicitly. The next step is training the model, and that's just as simple as model.train and then the samples. So the samples in this point would be those 2D points in space. And then finally, we predict the clusters that are coming out. So we call model.predict, and we're doing it on the same samples again, so we want to classify these initial data points. And we get out this vector of clusters, which tells us which ball each of the clusters belongs to. And if we run this on the data I showed before, then this is what we get out. So you can see that the model has sort of broken up the data into two halves, which sort of roughly represent those two balls that it came from. And each point is colored according to the cluster that it belongs to. Okay, so hopefully you've been somewhat convinced that that was fairly simple. 3 lines to do all that work is pretty good for machine learning. And the API for sort of all of the other models in machine learning aims to be as simple as that one. But machine learning is complicated. So as I said before, there's lots of models, lots of different ways to use them. And sort of one of the key goals of Rusk is to try and capture all that like complexity and put a simple sort of API over that, so it's easy for new users to sort of jump in and use things like that, while also sort of not obscuring too much the more complicated stuff for advanced users to take advantage of. So in short, Rusty Machine aims for ease of use. So yeah, how does Rusty Machine try to keep things simple? So the main part is using traits. There's sort of some other mechanics going into it, but sort of by using the trait system in Rust, we can try and sort of have sort of a nice modular layout to Rusty Machine and make it sort of easy to jump from one model to the other without having to completely rewrite huge chunks of code. So as I showed before, Rusty Machine uses that model trait as its foundation. So sort of all models implement this model trait. So when a user comes to use Rusty Machine, they're always using that same train predict thing, which, by the way, isn't like completely my idea. Other machine learning libraries have been doing this before, and it's a pretty common trick. And we sort of use traits to try and hide as much of this machine learning complexity as possible. So some key ways that we do that are providing extensibility at the user level. So if a user knows that they need something more than is offered in Rusty Machine, it's easy for them to sort of add that code on. And we also try and make things reusable throughout the library in as many ways as we can. So first I'm going to talk about extensibility. So yeah, as I said, we're using traits to sort of define different parts of the model. We want to make it really easy for a user to come along and sort of modify those parts without breaking all of the rest of the code. And Rusty Machine sort of tries to provide some common sensible defaults that people use often, but we try and make it easy for people to write their own implementations and plug those in. So I'm going to try and go over an example of extensibility without sort of diving too deep into the machine learning stuff behind it. So first I'm going to talk about a support vector machine. So I guess all you really need to know is that a support vector machine is a model that's generally used for classification. So it's similar to a k-means model in how it behaves. So the behavior of a support vector machine is governed by something called a kernel. So a kernel is essentially a function that obeys some particular properties that I'm not really going to spend too much time going into. But here's sort of roughly what a support vector machine looks like in Rusty Machine. So we have the struct svm, and we make a generic on a type k, which is implementing kernel. So this essentially means that the support vector machine sort of owns a kernel, and that kernel can be anything which obeys the rules or properties of a kernel. So this notation in the sort of angular brackets, k colon kernel, just means k implements the kernel trait. And this is what the kernel trait looks like. So the trait kernel just describes some function kernel which takes in the inputs needed for a kernel, which is 2 slices, and outputs a scalar. so by having sort of this layout, we're using the generic type to make it really easy for a user to come along and say, oh, I actually need a particular type of kernel for this application, and they can just implement this trait kernel and use it in all the same code. And again, this isn't something that's, I mean, it's obvious this isn't something that's only accessible in Rust. This isn't like some brand new novel thing. But Rust sort of gives us a lot more control and safety around this mechanism. So for example, by using slices in the kernel function, for those of you that don't know, a slice is sort of a pointer to an array. So by using a slice, we're telling the kernel function that it should borrow the data. So it shouldn't consume any of the data, it should just take a pointer to the data and sort of read from that only. So by sort of enforcing that behavior strictly in Rust, we make sure that when anyone else is using a kernel, they don't do something like consume the input data, which might be possible in other languages. And this could sort of break the model code if this was to happen. Okay, so I'm going to go on a tiny bit of a detour, and so I want to sort of show off something that, again, you could achieve in other languages, but works quite nicely in Rust. So kernels, as I said, are these functions that have these properties. And one of these properties is that if you have two kernels and add them together, then the resulting function from that, like as in functional addition, the resulting function from that is still a kernel. So it has all of the same properties and behaviors that a kernel originally has. So we can try and sort of capture this relationship in Rust. So to do this, we create a new structure called a kernel sum, which again is generic over T and U. And again, I'm using this where now to keep things a little bit tidier, but this means the same thing, that T implements kernel and U implements kernel. And then kernel sum just contains two of these kernels, K1 and K2. And then we're going to implement the kernel trait for kernel sum. So here's that kernel trait. So the implement TU kernel for kernel sum is saying we're implementing kernel for the kernel sum. And again, we have those generic trait bounds, so T has to be a kernel, U has to be a kernel. And then the kernel function we're now sort of explicitly describing. And it just sort of embodies that equation at the top of the slide. So it's K1 kernel on the input points plus K2 kernel on the input points. And sort of because of the way that kernels behave, we know that this is also a kernel. So the idea, like, why would we want to do this? So as I said, this behavior of sort of adding kernels together is sort of a nice one, and it's sort of something that quite commonly you want to combine two different kernels together to sort of achieve a slightly different behavior on your support vector machine or another model. And by sort of implementing this kernel sum trait, we can make it really easy to do this like straight out the box. We don't have to worry about writing any additional code. We can just use existing sort of in-library kernels and combine them together. So if we wanted to use some complicated kernel that's the addition of a polynomial kernel and a hypertam kernel, we just define our two kernels above, and then we'd have the sum kernel be equal to the polynomial kernel plus the hypertam kernel, and then we can just plug that sum kernel right into the SVM. And so again, this isn't something that's impossible in other languages, but in Rust we sort of keep all those guarantees about how should this new kernel borrow the data, how should it, how does it behave with ownership and borrowing. And this is something that I think is a really nice, neat thing to have, especially because you can do it so safely. Okay, and I'm going to move on from extensibility to reusability. So reusability kind of, at first, maybe seems like the exact same thing as extensibility, and maybe arguably it is. But I think that what I mean here is that before with extensibility, I was describing sort of taking a trait or an object that implements a trait within a single model and building on top of that to get more complicated behavior. Whereas by reusability, I mean that we can have sort of the same trait used across multiple different models and nothing breaks. And I mean, you can try and break things, but the compiler will shout and scream at you, which is nice after a while. So I mean, yeah, this is definitely possible in other languages again, but Rust makes it really easy to do. So the idea of reusability is that we have these components that can be swapped in and out of the models, and we can easily make new models from existing components as well. So I'll go through an example in a moment, sort of describing how if a user wants to make use of something in Rusty Machine, they can just sort of put it out of the box, and relying on the sort of strong enforcement of that trait, they can sort of ensure that everything will work roughly as expected. Yeah, so just another thing, again, I've sort of touched on it a few times now, but again, it's something you can get in other languages, but I think in Rust it's nice to sort of be sure that if I'm using a kernel function in another model that I've just created, that it won't consume data. It will like borrow the data instead of consuming it and behave nicely with all these various safety guarantees we have. Okay, so a reusability example. I'm going to talk about gradient descent solvers. So there are probably, some of you have probably heard of gradient descent. I'll sort of briefly describe what it is and why it's important, but we won't go into too many details. So we use gradient descent to minimize a cost function. So what do I mean by a cost function? You can imagine back to our earlier example of having rent. In that problem, we're trying to predict what our rent will be. And obviously you can sort of imagine there's a true value for what our rent actually is, and we're trying to minimize the distance between the value that we predict and the true value itself. So you could define, for example, a cost function to be the squared distance between our prediction and the actual value. And that's a pretty common cost function, actually. So the idea behind a gradient descent solver is that in Rusty Machine is that we have it implement this trait. So this trait for gradient descent algorithms is poorly named optim algorithm. And optim algorithm is generic over M, which is optimizable. And it has this optimize function. So that's a bit of a mouthful. It looks pretty messy up on the page, and that's even after I've removed some things. But essentially, this is saying that the gradient descent solver has the ability to optimize a model. So we give the gradient descent solver a model and a set of sort of initial parameters, and it will do some magic under the hood, and it will return an optimized set of parameters that sort of minimize our cost function as well as possible. Just sort of talk through a couple other pieces of notation here that I maybe skipped over. So the vec part the vec F64 that's coming out of that arrow on the right, this just means that it's like an array of floats. So this is our parameters coming out that have been optimized after we've run gradient descent. So the optimizable trait in this case is implemented by a model which is differentiable. So by that I mean that the model has a cost function and we can differentiate that cost function. So I'll sort of run through this with an example using that sort of distance cost function I explained before in a kind of roundabout way. So I'm going to sort of go through the flow, creating a new model using gradient descent optimization, and hopefully convince you that it's pretty easy to use. It's a lot nicer maybe than sort of implement this stuff from the ground up yourself. So the first thing we're going to do is define our model. So I'm going to define a really simple model, which is called the x squared model. So the x squared model represents a cost function, which is f of x equals x minus c squared. So that's that sort of Euclidean distance in 1D space. So it's the distance from the point C. And the x squared model just takes in an argument c, which just represents this point. So the idea of if we wanted to minimize this cost function, we're trying to get x to be as close to c as possible. So you can sort of think of this model as learning the value of c. So we give the model a value of c, and then by plugging it into the gradient descent optimizer, we're trying to sort of learn what that value of c is. Again, as I said, it's kind of a convoluted, silly example. We know what the value of c is, but it sort of represents what we're doing a bit more in the real world. Okay, so once we define our model, the next step is implementing optimizable for the model. So as I said, optimizable is something we implement for models that are differentiable, have differentiable cost functions. So it has this function compute gradient. So it takes in the model, which is the sort of the ampersand self, and then it takes in a set of parameters, which is a slice, and it returns a set of optimized parameters at the end, which is a vector which has the same dimension as the slice coming in. So in this case, it's really easy to compute our derivative of our cost function. We just differentiate x minus c squared, and we get 2 times x minus c. So yeah, just say in this case, the parameters would just be one-dimensional, and it's just going to contain the value x inside a slice. Yeah, the vec exclamation mark thing is something called a macro in Rust. It basically means create a new vector with this data inside it. Okay, so again, this isn't super useful on its own, but now we can sort of use optim algorithm to do some fun stuff. So using optim algorithm out of the box, we can compute these optimized parameters. So the whole code all at once is this. So this creates the new model x squared with the value c, defining that cost function. It teaches us how to differentiate that cost function. And then finally, at the bottom, we're sort of using this in action. So the first line underneath the implementation part is let x squared be a new x squared model with the value c being 1. And then we're just creating some starting point, which I've just set to 30. It could be anything. And then the next line creates a new gradient descent solver. So let GD equal gradient descent default, just creates a new gradient descent solver with whatever the default settings are within Rusty Machine. And then the last line is let optimal equals GD.optimize. So this is running that optim algorithm trait. And the hope here is that the optimal value we get out will be as close to 1 as possible. So by sort of using this setup and just taking advantage of the gradient descent that's already in Rusty Machine, we should get an optimal value out that's 1. So it's kind of useless, right? No one's really going to be using the optimizer like this, but I think sort of those of you that are familiar with machine learning, having this sort of trait set up for the gradient descent algorithms makes it really easy to sort of implement a new algorithm that does rely on gradient descent, something like neural networks even, and just plug in this gradient descent solver at the last step to do the optimization part. And of course, it's really easy as well for us to implement different types of gradient descent solvers, like stochastic gradient descent, various other things that people are probably familiar with. Okay, I think that's about as like maths heavy and theoretical and obscure things get. So I'll sort of move on to a second part, talking a bit more about sort of why Rust is valuable and sort of a bit more about how Rusty Machine works, at a high level underneath. So this is just a list of things that Rusty Machine can do. It's just sort of, I guess it's a common question to wonder, what have we actually covered here? And it's a fair amount of stuff. It's not to say that all these things are sort of feature complete and ready to go into production, but they're sort of working versions of all of these different models and algorithms. So I think a really important part of Rusty Machine is the linear algebra part, which has now been sort of split out into a new crate called RuleNalg. So the reason why this is important is that sort of when I started creating Rusty Machine, I wanted to make a library that works out of the box, so something that doesn't have all these heavy dependencies like BLAS, LAPACK, CUDA, whatever else, like all the other machine learning libraries that you're using nowadays. And to do this, I had to sort of have my own sort of completely Rust linear algebra stuff written out. And this is where RuleNalg comes in. So RuleNalg provides linear algebra that's implemented entirely in Rust, so running no external dependencies at all. So yeah, why RuleNalg? I mean, there's some history behind why this thing exists. So when I first started development, it was kind of unclear whether there would be any other options that would be a good fit for what I wanted. There was no sort of clear Rust linear algebra library that worked in high-dimensional spaces that machine learning is sort of predisposed to. So, I mean, yeah, RuleNalg sort of provide that ease of use and out-of-box stuff. I mean, ease of use for the user. Writing it was a nightmare. But it sort of makes it a little bit easier for the user to just get running right out of the box without any other work. And of course, like, Rust is a really great choice for implementing linear algebra. So anyone that's played around with sort of low-level, like, C libraries, linear algebra, it's difficult and messy, and like there's all these weird routines and stuff. I mean, Rust just makes all this stuff like really nice and friendly. It takes some work, but it's really pleasant to use. I've just sort of inserted like a quick note on error handling here. Just at the last minute, I realized I hadn't spoken about it. So Rust error handling is really amazing, and it's like fantastic for linear algebra especially. So we have sort of a lot of procedures in linear algebra that can fail, and there's just lots of ways where we just can't help them failing. And sort of Rust result captures that idea kind of perfectly. So using a result here, so the result matrix error part, a result in Rust communicates that a method might fail, and we could expect it to fail. So using a Rust sort of explicitly says, you know, if you try and inverse a matrix, it might not work. I mean, obviously, again, it's something that is present in other languages, but for those of you that have used Rust, I'm sure you're familiar with like how nice this sort of result chaining stuff can work. Yeah, so this is what the inverse function for RuleNalg looks like. It returns a result of a matrix, and then the error will tell you sort of what went wrong. Is it non-singular or anything else? Just another quick point is that, yeah, although error handling is fantastic, I've not made very good use of it within Rusty Machine so far. So RuleNalg is pretty good, but Rusty Machine's a bit rough around the edges. So if anyone wants to help out with that, that'd be awesome. Okay, so what does RuleNalg do? So right now, RuleNalg has some data structures, matrix and vector, as well as, I haven't mentioned them here, but there's some matrix slices as well, which are sort of analogs of slices in the standard library. So they sort of provide sort of views into a matrix, letting you borrow the data without consuming it or owning it. They have sort of basic arithmetic operations, and we're using in-place allocation wherever possible, which is another really nice thing. And then some, I say standard decompositions, but some of these took a lot of work. So we have inversing, eigen decomposition, singular value decomposition, and a few other things built in. Okay, I'm going to talk quickly about why Rust is a really good choice. Am I doing okay for time, by the way?
Yes.
Okay, cool. I'm going to talk quickly about why Rust is a really good choice. I mean, hopefully I've sort of alluded to that as I've gone through. But I think the key thing to me are that you know, the trait system is really fantastic. Error handling is amazing, even though I've not used it that well. And obviously, Rust has that blazing speed, which is really great. I mean, sadly, Rust Machine needs some more work, but I think the future looks really bright for having sort of really high-performance code in Rust. Sort of a couple other things on top of this. Historically, with sort of machine learning stuff, we sort of have this pattern of prototyping in a high-level language like Python, and then rewriting performance-critical parts for our production code in like C or C++. I think Rust can sort of fill this really nice space of doing both. So it's, as I've hopefully shown, it's fairly quick to get a prototype up and running in Rusty Machine. And maybe with some more work, it'll also be possible to extend that to, you know, a performance-focused, production-ready piece of code. Another thing is that, I mean, I'm sure for those of you that have been developing in Rust, it just provides a lot more insight into what you're doing. So this is from a developer's point of view, but sort of working hard to get these models working in Rust was like a great way for me to learn a bit more about how the models work underneath, you know, focusing on when does the model need to own its data, when's it more efficient for a model to sort of borrow a piece of data. It was, yeah, very, very challenging at times, but like a great learning experience. And that's the reason for this. Yeah, most importantly for me is the fact that we have sort of safe control over memory, which I think is really, really valuable for machine learning, especially when you have these models that have huge amounts of data. It's really great to be able to control explicitly how that's being used without delving into some really ugly, likely to break code. So another pretty common question is, when would you use Rusty Machine? So right now, not in production. It's experimentation, non-performance critical applications are maybe okay. I mean, these algorithms work, but they're not sort of numerically stable. They're not state of the art. I think that in the future, Rusty Machine will hopefully sort of fill that space of quick, safe, and also powerful modeling, which is certainly available in other languages, but I think Rust has the power to sort of provide that without external dependencies, though we're not quite there yet. I was going to talk sort of quickly about Rust and machine learning in general. So I think that Rust is really well poised to make an impact in the machine learning space. I think it's fairly obvious the things that sort of Rust offers and its selling points are things that machine learning can really take advantage of. I think on top of that, there's some sort of really excellent tooling built into Rust. I mean, it's a modern language, and sort of that tooling is going to be really, really valuable just in the machine learning space in general. And sort of another thing that I felt the benefit of really early on is you sort of get, I mean, thanks to LLVM and the sort of design of Rust, you get performance with minimal effort compared to if you've sort of been coding these things in C++ and other languages. I mean, once you're past sort of wrestling with the borrow checker, it becomes really quick and easy to get something that's vectorized and borrowing data efficiently and running quickly. I think there's obviously some downside. I'm not saying that Rust will take over the machine learning space. I think there's some things that right now, at least, it doesn't do as well. I think a big part of that is exploratory analysis. So it's quite common in machine learning when you're approaching a new problem, sort of want to play around with the data a bit, quickly sort of see what the data looks like, do some analytics and visualizations. I think that's going to be something that right now is pretty difficult for us to do. And languages like Python sort of really hold their own there much more effectively. So what's next for Rusty Machine? So first of all, as is always going to be a focus, optimizing and stabilizing the existing models is really important. So another thing is providing optional use of BLAST, LAPACK, and CUDA. Just quickly, I'm not sure if I've sort of said, but so these things sort of not all of them. BLAST and LAPACK are these old libraries, written like the 70s or something, that were written in Fortran, and they're sort of provided bindings in other high-level languages. And these are sort of the de facto, you want super fast information multiplication, you want super fast linear algebra routines, these are the things you use. And I think it's kind of silly to try and fight that. I mean, there's literally decades of experience, research, and expertise that have gone into building these things. So I think it's definitely very, very useful to have those bindings there. The only reason I haven't so far is that I just feel like it was sort of more valuable to have that ease of use and just things running out of the box, at least for now. And the other thing is addressing sort of the lack of tooling around Rusty Machine. And by lack of tooling, I generally mean data handling and things like that. So right now, sort of all that is left to the user. There's no sort of built-in, I want to load a CSV, I just run this one function and it comes in like you have in NumPy. So I think that's sort of something else that'd be really nice to see coming in. And just quickly, a couple of things I'd like to see from Rust. I think specialization, I think most people are looking forward to that. The ability to sort of overwrite these traits in particular instances for performance reasons would be nice, and it would also sort of help keep the code a lot cleaner. I think I've sort of said quite abstractly growth of float and complex generics because I have no idea how it should look. But it's kind of difficult right now to sort of do things like eigen decomposition and singular value decomposition where you might put in floats and then get out complex values. I think it's quite difficult to capture that in Rust right now. And it's sort of a continued effort from the community. I mean, it's hard to say anything bad about the community. It's really great. The drive and enthusiasm is amazing. And it's awesome to sort of see new things popping up all the time that are making using Rust easier. So a quick summary. Machine learning done quickly. So hopefully I didn't confuse anybody too much. I'm just sort of briefly explaining what machine learning is and why we do it. Spoke about Rusty Machine and ruling out a little bit. I have this page that has some contributors on Rusty Machine. So for those of you here tonight, thank you very much. Yeah, and thank you. That's all.
We have time for a few questions. Use the microphone.
Hey.
Those graphics you showed, did you draw them with Rust?
No. I do them using Python. Yeah.
What's the current perf hit as compared to using something more traditional like LAPACK or Atlas for your BLAs?
So I don't have those numbers available for the whole library, and sort of in general, like if you're running a model, I don't know what that looks like. But for matrix multiplication, thanks to some work by Bluss, like it's pretty good. So he sort of built this library called Matrix Multiply, which sort of handles, like in Rust, some really nice matrix multiplication routines. And I mean, maybe the number I say will sound really bad to some people, but it's sort of like twice as slow in worst cases, which, I mean, for anyone who's used Blast in the Pack, that's pretty amazing. I mean, getting that is really good. And I think, yeah, I've sort of tried a little bit of parallelizing that and using sort of multi-threaded stuff to speed it up, which was somewhat impressive as well, but hasn't made its way into the library yet. So I think in general it's not terrible, but it's not to say we don't need them. I think they'll still be like pretty necessary to use the library.
Cool, thank you.
Will you please say once more what it is that Rust is not currently good at? It was exploratory.
Yeah, sorry. So, I'm trying to find my notes. Right, sorry. So exploratory analysis.
Right.
So by this I mean sort of when you're tackling a new machine learning problem, it goes like this. You've been given a data set and you want to find some insights about it. So the first thing you do is try and dig into that data and sort of see what does the data look like, what are the sort of key important features of the data. I think that right now doing this in Rust is just a lot slower than it would be in other languages. So the tooling in Python, for example, is just like, it's very well established and built up to do that. And I think it's quite hard for Rust to compete with that right now.
And does this have to do with a well-developed library, or what is it specifically that could be developed in Rust?
So I think the key thing that sort of most people would argue is probably the lack of a REPL, so the ability to sort of have its own command line to sort of do this stuff. I think in Python that's particularly valuable, and obviously that's something that Rust can't offer for a while yet. But I think there definitely could be some Reusability libraries that would make that sort of easier. Whether it would be enough to sort of take over that big dominant space by Python, I'm not so sure.
Thank you.
Okay.
So in some of the traits that you showed, I think self was borrowed mutably, and in other traits, self was borrowed immutably. And given that you're designing traits for like implementations that you don't necessarily know ahead of time, I'm wondering how you end up thinking through like when to do which.
So with difficulty, if I'm being honest. But so I think in many cases, I'm not sure how long it takes to go back to the beginning here, but in many cases it sort of follows quite naturally from what we're trying to capture in the machine learning space. So if I can go back to our very first example, there is a reason for this madness. Right, okay, so in this case, like train takes a mutable reference. So when I sort of first gave the definition of train, it was that it sort of transforms our model to sort of map inputs to outputs. So in this case, it's sort of quite natural to let it be a mutable borrow. Whereas in other cases, we sort of don't need that mutability. I think in general, it sort of comes down to me deciding that we don't need mutability here, so why provide it? That's sort of generally the practice, but I think there are lots of cases where it sort of follows quite naturally. Yeah, I'm not sure I can give a better answer than that.
So why did you develop this? Is this just a labor of love, trying to start a business doing it? What's your, just for the community?
So it's not a simple answer. Originally, I sort of wanted to try learning Rust. And I was like, well, I know a lot about machine learning. I guess it would be nice to sort of transfer that knowledge into Rust, and hopefully my love for machine learning will help sort of push me through the tough patch with the borrow checker. It did, but so what ended up happening is I was like, oh, I guess I need some linear algebra. Let's just look up the linear algebra library. Oh, there isn't really one that just works out the box. I guess I'll just write some simple stuff myself. And then sort of by the time I finally got to the machine learning part, after building up like all this stuff to get inverses in Rust, I was like, well, I've spent so much time now, I may as well just carry on. So my attempt to sort of learn Rust and take a go at some like server-side, like low-level systems programming sort of ended up in me spending all my time writing a machine learning library. And at this point, it's pretty much a labor of love. I mean, I'm really enjoying writing in Rust. It's really, really fun. And it's also great to sort of learn some machine learning stuff that I maybe don't know so well right now. It's sort of cool to explore that in a language that sort of forces you to really understand what's going on under the hood.
Any other questions? All right, well, thank you.
Yeah, thank you.
Next up, we have Amit. Let's see. you want a split screen or?
No,
Oh, you just have
just regular.
old-fashioned screens. Ah, but it's on the wrong window. But, well, there, and okay, and you should be there.
Cool.
Thank you. Please give Amit a warm welcome.
Thanks, you guys. So I am going to tell you about Talk, which is an operating system for microcontrollers. And by microcontrollers, I mean these little computers that have extremely limited resources. So we're talking about things that we would like to be able to run at like an average current draw of under 50 microamps. Just like for comparison, your phone runs on an average of like 100 milliamps. So what is that, like 3.5 orders of magnitude? They have very limited amounts of memory, and they need to meet relatively tight timing constraints. Is there a way to?
Yeah.
Okay.
Sorry.
I was gonna come and suggest fixing this to Google page. There.
Okay, great. You're my savior. Thank you. And so to meet these constraints in sort of an operating system environment, what Talk needs to do is to rely on a different isolation mechanism than sort of traditional processes, traditional hardware protection. And we basically use the Rust type system to do most of the isolation in the kernel, and then like the rest of the memory is used for a couple of applications, like a handful of applications that just use hardware protection. And this kind of highlights this tension between the granularity at which you can do isolation and the resources that you end up consuming because of this isolation. And we resolve this tension in Talk by pushing everything into a single-threaded asynchronous event system for doing concurrency, and then using the type encapsulation of Rust, of the Rust type system and module system to get isolation. Okay, so I want to start by sort of motivating, why we are building an operating system for microcontrollers in the first place, and why this operating system should care about doing isolation and protection. Okay, so microcontrollers are everywhere, all the way from things that are primarily designed to, convince rich people to keep making money so they can buy like fancy lamps and stuff, all the way to actually necessary things like medical devices and so forth. And then the existing sort of, quote-unquote operating systems that tend to run on these devices aren't really operating systems in sort of the traditional way that we think about that. And I'm not saying that to like put down existing operating systems. They just don't have the same kinds of goals. So, they typically don't really do any sort of separation between the core kernel code and drivers and applications. They're just sort of all like this one monolithic piece of code. And they don't expose any isolation mechanisms to let you do isolation on your own. And so really the operating system is more of like a library that helps you program these things with a little bit more ease. And so kind of the mental model that you want to think of is like Ruby on Rails for your defibrillator. And this model kind of comes out of how, what the traditional thought is of how we build embedded systems, but it doesn't really apply to how embedded systems are actually built anymore anyway. So how are they built? Well, first we're going to take some set of sort of off-the-shelf parts, like a microcontroller, maybe some radios and some sensors and actuators, and we'll stick them on a custom board for our product or our development kit or whatever. And then we'll choose some operating system, quote unquote, to build our software on top of. And then we're going to grab a bunch of drivers for all of these off-the-shelf components that we had. So, we might take like a temperature sensor driver from Adafruit, or like a Bluetooth driver from Nordic, et cetera, et cetera. It might come from like a variety of sources. And then we'll build our application on top of these drivers and operating system. And these applications are kind of hand-rolled code. They might do relatively complicated thing like encrypt data that we're sending over the network, or machine learning like we just learned about, etc. And then finally, we'll take all of this code that we cobbled together and wrote ourselves and optimize it for basically everything except for security. And so, the result is that embedded systems are really built just the way that other systems are built. They're built from reusable components. And reusable. I don't want to give reusable components a bad name. They're good. Like, we need these, right? Because it means that we don't have to reinvent the world every time we build, like a silly little, remote controllable light bulb or something. But we're mixing code from a variety of sources, and we don't have any isolation mechanisms like we would in a traditional system. And then we're optimizing for a bunch of stuff that's complicated to optimize for and is not security. And so this is really a recipe for bugs. And the question is, like, what happens when there is a bug in one of these components? And the answer is that all bets are off. If there's a bug anywhere, then nothing is safe in the system. Okay, so in the rest of this, I want to first talk about why sort of the traditional process model that we tend to use for isolation in most systems isn't going to work for embedded microcontrollers. And then I'll show you kind of an overview of like how TOC is architected, and then I'll describe capsules, which is sort of the basic isolation mechanism in the kernel that we use to address this. And then I might have time to talk about this I think pretty cool mechanism called grants, but that is particularly cool because it I think shows off some really neat features about how you can use sort of really basic low-level primitives in the language to guarantee high-level system stuff. And then I'll show you some numbers that prove that doing language isolation can be much more efficient than, I don't know if they prove it. They argue or whatever that like doing isolation at the language level can be much more efficient than using processes. Okay, so why are processes not going to work? In a traditional process isolation model, we're basically going to split our system into a bunch of different isolated components, and each of these components will effectively get its own region of memory. And they, each component can't really reach into the other component's memory and touch anything. And so each of these red boxes is kind of its own little world, and it can more or less pretend that it's running by itself. And if they want to communicate, in order to interact with each other, they'll do so over some sort of actual messaging communication mechanism like IPC on something like Linux or something like that. Okay, and this model is in general pretty nice because it does sort of two things for us. It gives us isolation, but it also provides this nice concurrency model that also enables parallelism. And in particular, it's this like concurrency model that we don't really have to think of about concurrency all the time, so we get to write this nice sort of sequential code. And it's also a model that's convenient to enforce both with like language runtimes and hardware. So there's kind of good reasons why most systems use something like a process model or some variant of a process model to do isolation. It's a good model. But the problem is that there's a resource overhead associated with every unit of isolation, right? So every time we break apart another component of the system and put it in its own box, in its own process, we have to allocate some memory that's only going to be usable by that process. And every time we want to communicate between components, we have to do some sort of context switch. Like on Linux or whatever operating system is going to be an actual context switch. It might be a more lightweight context switch between like threads or closures or just swapping stacks. But there's some overhead to sort of communicating between the components because we basically have to swap which domain is active at the moment. But remember that these systems that we're targeting have like very constrained resources. So at the lower limits, we may have as little as only like 16 kilobytes of memory. In some cases less, but actually our operating system doesn't support that either. So let's pretend like this is the lower limit, and relatively tight timing constraints, which on the one hand means that like we just can't fit that many things into memory, and then on the other it means that there's like a relatively high sort of practical cost from the application's perspective of like incurring this overhead every time we want to communicate. So let's look at how this might play out. Suppose we have this like little tiny 16 kilobyte device. Well, if we have one component on there, maybe we only need to allocate like 4 kilobytes or something like that for just a stack, just for that one component. And so we can maybe fit 2 or 3 more in there. But as soon as we want to split up our system to more things, we're just going to run out of memory, right? It's kind of there's just nowhere to put it. And so processes sort of fundamentally make us trade off the granularity at which we do isolation and the amount of resources we consume. So we could totally have like one application in one monolithic kernel and we could probably fit that in 16 kilobytes of RAM. But as soon as we want to do sort of more granular isolation within, untrusted kernel components, we're very limited in how much we can do that. Okay, so Talk tries to resolve this tries to resolve this particular challenge. So how do we isolate concurrent components inside the kernel in our case without having to incur an overhead for each new unit of isolation? And the sort of key idea is that we're going to use a different concurrency model that's just a single-threaded cooperative event system, and isolate components just using the Rust type system. So we no longer have this notion of like totally isolated regions of memory that are only usable by one component. Instead of they just all share the same memory. And this is at a high level what the operating system looks like. So at the top we have more or less traditional processes. There's this grant region which I may or may not talk about if I have time, but otherwise these processes kind of look like a process would look on like Linux or whatever traditional operating system. But the kernel has numerous components called capsules. And those are effectively units that only sort of exist before compile time. Once you compile them down to machine code, these barrier between the capsules, more or less go away. There's a little bit of caveat to that, but effectively the machine code looks very similar to what it would look like if you were just writing sort of a monolithic kernel in C. Right. So as I mentioned, the concurrency model is event-based. And in particular, what we're going to do is effectively, anytime we have some actual event from the world coming in as a hardware interrupt, we'll just enqueue those all into the main kernel thread, and sort of run them as they come in. Dole them out to whichever capsules are specified to process them. And then importantly, like the capsules never block on I/O. So every time we get to a point in the capsule where we would otherwise sort of wait for let's say sending a packet to complete, we'll instead just return back to the main event handler and say like let me know when this packet is done, but like meanwhile let other capsules do their thing or just go to sleep or something. But then, once we're actually running in one of these capsules, the way that we communicate between components is just by calling functions on other capsules. So we have sort of direct references to other capsules, like it's literally just Rust references to another value, and we're just going to call functions there. And then we get isolation because the Rust type system, gives us this mechanism to effectively do things like hide private fields or force interaction, sort of across module boundaries only through like a tight interface from a function or something like that. So you can sort of constrain even further than just which fields are exposed or not. Okay, so what do these capsules look like? So the capsules are basically the things that live inside the kernel, as I mentioned. The kernel itself is sort of divided up into, hopefully as small as possible, this trusted computing base. There's some things that are unsafe that don't necessarily have to do that much with the capsules. Like the process scheduler has to do things like twiddle hardware registers, and so that kind of has to be written in not assembly, but almost assembly. But for the most part, you can think of the core kernel as basically just taking things like hardware-mapped memory registers and just like casting them into a Rust struct. But above that level, more or less everything is basically to some degree untrusted and lives in these capsules. Okay, so this is an example of a capsule. This is a pretty simplified, but still gets the idea across, I hope. Example of basically a driver for a light sensor on one of these microcontrollers. So let's look at this. So we have this data structure called light sensor, which is modeling the functionality that we need here. And the first field is just this reference to basically just a pointer to an I2C device. I2C is just a communication protocol that a lot of microcontrollers use to communicate with sensors and stuff like that. But this could be like whatever, a TCP device or something like that. It doesn't really matter. But this I2C device is also a capsule. right? So if we want to do something like send a packet over I squared c, we're just going to call a function, and that'll get compiled down to a jump instruction or something like that. Just like the same thing that would happen if we were just writing this as a monolithic thing. And then it of course also has other fields that store things like the state of the protocol that it's in, etc. Sorry. And the last bit is notice that the fields of this structure are not public, and that's true for the I squared C device as well. In general, many of the fields are not public. So this is an example of how we're using basically the module boundaries here to enforce that even though I have sort of like a direct reference to the I squared C device, or I might have a direct reference to the light sensor from some high level driver, it still doesn't mean that I can't do anything I want with it. I'm like forced to go in the case of the light sensor. I'm forced to go through this like relatively narrow interface of like whatever start reading the lux, the light measurement, right? Which means that I can't just like arbitrarily change the current state of the protocol to be some incorrect thing, right? Like I have to go through this narrow interface. Okay, so the result is that capsules are sort of untrusted for access, meaning they're only trusted to be able to access resources that they're explicitly given, right? So they might be trusted to access like a virtual I squared C device and go through a particular interface, but they can't just like reach over into some random place in memory and twiddle a bit or something. But they're not trusted for liveness. And this is sort of the consequences of the threading model, right? So we're sort of relying on capsules to yield the CPU when they're done doing whatever like small amount of work they're doing. But because we don't have something like a process model where we can just sort of decide to switch away to another task and our state is going to stay the same in the first one, we can't just like decide to preempt a capsule in the middle. And in fact, if a capsule decides to like spin on a while one loop or something, the system is screwed. So don't do that if you're writing a capsule. Do I have time to do memory grants? Barely. Okay. So I said that the process model is more or less traditional. One sort of difference here is this grant region at the top. That's just this little it's the gray box that says grant in it. The reason for this is that one of the constraints that we have in the kernel, and is pretty typical for microcontrollers, is we want to totally avoid dynamic memory allocation in the kernel. That's a sort of a typical engineering practice in microcontrollers, just because there's relatively limited memory, and it's with heap allocation, it tends to be hard to predict whether or not you're going to run out of memory. So kind of like best to avoid it if we don't have a good way of like debugging this at runtime or something, because it's some defibrillator that's in my body that I can't get a core dump from or something. Anyway, but if we have multiple applications and if they're dynamically changing, it can often be convenient to nonetheless dynamically allocate stuff. So we have these grant regions, which are basically allocated in the process's memory, but are given access exclusively to some kernel capsule. So the process doesn't have access to it, but the capsule is basically allowed to sort of borrow that memory. And not in the Rust sense of borrow, but in like the normal sense of borrow, to borrow that memory to use for tasks that are associated with the process. But like an important property that we want is if a process crashes and we have to restart it, we shouldn't have to wait until all of the capsules that might have had access to like some part of the grant region are done using it, and we don't have to go through like some complicated check to like count all of the references to some process's grant region. We want to be able to just wipe all of this memory clean as soon as the process dies, so that we're not, again, using up a bunch of memory that could be reused for a process. Okay, this is all what I just said. So the things to remember are the one thing to remember is that we have a single-threaded execution model that will come into play as sort of our system constraint that we get to leverage to get a higher-level property. Right, so these are all the things I already said. Okay, so we want to enforce 3 invariants. The first is that allocated memory doesn't let capsules break the type system. That's obvious, but important to state. Capsules should only access pointers to process memory in their grant region while they're alive. This is, again, a consequence of the fact that we want to be able to reuse that memory as soon as the process dies to restart the process or to put another process there. And the core kernel needs to be able to reclaim that memory as soon as the process dies. Okay, the problem is that like processes can die dynamically, right, at runtime, and we don't know how to predict that ahead of time. But Rust determines memory reclamation, so it injects sort of the equivalent of malloc and freeze statically. That's the whole point of the borrow checker, is to figure out exactly at compile time when I get to free things. So there's kind of this mismatch here. But the observation is that we actually can kind of use the type system to enforce very simple properties. But if those simple properties interact with our system architecture in just the right way, then we can actually achieve sort of higher level safety goals like what we want for the grant regions. So this isn't the implementation, but it's the entire interface for grant regions. And actually, we can look only at the types of these structures to see that we can get the properties that we care about from grants. Okay, so we have three structured here. The owned structure is basically our version of box. It's basically the box type, but that only has to do with dynamically allocated memory from grant regions. And then this grant structure is basically something that that a capsule might have a reference to, and you need to basically enter a grant using this enter function, or this enter method, in order to actually get a reference to the thing inside. And when you enter it, basically the grant yields the grant region structure to a closure that you pass in. And importantly, this closure is constrained by this really gnarly type, f colon the fun ones type, right? And the important bit here is that the lifetime on the reference to owned in the closure is what's called existential. And basically what that means is that the closure doesn't get to assume anything about the lifetime, meaning it has to let go of that reference before it returns, right? So what this, for tick B means is that we know for sure that nothing is going to escape, that the own type is not going to escape the closure. And then the allocator is basically the way that we allocate extra own stuff once we're inside of a grant region. Okay, so what are the invariants that we know from these types? Well, as I said, we know that the tick B lifetime is existential. So once I've returned from the enter function, I know that nobody has a reference to the thing that to the own type, to the thing inside of the grant region. I also know that allocator and own don't implement copy. So that's important because the only thing I can return from the closure is something that's copyable, right? So I know for sure that I cannot return an allocator or an owned from the closure, right? Because it doesn't implement copy. And finally, the allocator and enter, the allocator type and the enter function are the only ways to create an owned. That's kind of by construction, because we've hidden the constructor to owned, and we only sort of give access to it through these two mechanisms. Okay, and so we know that own types can never escape the closure that's passed into enter, right? That's the thing that we cared about. So we know that. We also know that when the process schedule is executing, all the capsules have returned. Why do we know that? Because we're in a single-threaded event model. The process schedule runs sort of at the bottom of this, or at the top of the stack, whatever, at the very beginning. So it's just like an invariant of the system that we've designed. That like when the process schedule is running, we know for sure that it's that there's no sort of ongoing capsules, that all capsules have returned. And so that means is that when we've noticed that a process has died in this sort of process schedule in the reclaimer, we know that we can reclaim all of its grant regions, right? We know that there aren't any current capsules running that have sort of outstanding references to any grant regions. We know that the own type, that the stuff inside of the grant couldn't have escaped anywhere else because we enforce that in the types. And so we can just wipe away the grant region by like overwriting it with zeros or decrementing a reference count or something like that. And then basically you can think of the stuff inside of there being like deallocated lazily. When I try to enter the grant again, there's just not going to be anything there, so I'll get like the default value or whatever. Yeah.
Yeah. So does this mean that you're not using time? Oh, you use them So does that mean that you're not using time slice scheduling, so the scheduler can never be run because of an interrupt? Okay, cool.
Yeah. So that inside the kernel is totally single-threaded. So we technically have interrupts, but like all interrupts do are enqueue the interrupt event for the main scheduler to then pull. Yeah, and that's super important. Okay, so currently Talk runs mostly on this one platform. The details aren't super important. And in the implementation for this platform, there are, I haven't counted exactly, but at least over 100 capsules. So kind of the point of that is to imagine like how would you do this with processes, even if you had like 256 byte stacks, which is tiny, like you'd very quickly run out of memory to actually run your application. And the whole kernel takes up about 7 kilobytes of memory, a ton of flash, but we're working on reducing that. And so there's room left for about 7 processes with 8 kilobytes of memory each. You could twiddle that around if you wanted to, and we have drivers for sort of high-level things. Okay, and the high bit is that in some cases, like you really need to use something like a capsule if you care about doing isolation just for performance reasons. So this is sort of a comparison of the time it takes to do sort of a high-level operation that's communicating across units of isolation, depending on whether the isolation is in a process or a capsule. So if you're doing something really low level, like twiddling a pin on the board, and you have to do it quickly, like for example, if you're doing a software implementation of some communication driver or something like that, you can't do it with a processor. Like with a process, it's going to take you, I think this is around 8 microseconds for each time you want to like turn a bit on and off. And if you have to do this at like 100 megahertz, you're screwed. Like one time that you twiddle the bit, you're already done. Whereas with a capsule, again, it compiles down to just a function call, which is probably going to get inline. So this is like literally 6 instructions, which is like a pointer dereference and a store or something like that with a couple checks. But like in other cases, it doesn't really matter that much. Like if you're sending a large string over a serial port, which is the 2 bars on the very right, then sure, like doing this over a process takes longer, but notice the huge gap between the bottom part and the top part of the graph. Like sending a large string over, using DMA or something over a serial console takes forever, and so like it doesn't really matter that we would incur some penalty by using a process. So, the point is just that there are cases where you really need this level of isolation to be really cheap, and there are other cases where it matters less. These are just some hard numbers comparing the overhead of capsules with processes. The high bit is that there still is some overhead for doing things like capturing events from interrupts, and the reason is we fundamentally have to be, in order to enforce all the invariance that we want, we have to be single-threaded, and so we're giving up on basically being able to like immediately respond to events in the hardware, which would take effectively no time, like only the amount of time that the hardware takes to respond to the interrupt, versus what is 8 microseconds relative to that, like 4 orders of magnitude longer, even in just a capsule. But of course, it's like even worse in a process. And this is an application that we built, blah, blah, blah. Okay, so there's a bunch of things that I didn't talk about, partially because I don't have time, partially because like we may not have the answers to these yet. So I think that the two really hard questions to answer as of yet are okay, so we can use in principle the type systems to sort of design these interfaces that would give us isolation, but like what are the principles that you use to make sure that this interface that you're exposing is on the one hand actually safe from a language perspective? It's actually very easy to design interfaces, if you're not careful, that would allow you to break the type system. And then beyond just like the language level safety, how do you actually make these things secure? So like if I expose a type safe interface, but that nonetheless inadvertently lets some random driver like read your crypto key or something like that from the hardware, like you haven't really done very much. And we don't have good answers for that yet. I think that that's like a generally speaking hard question to answer in general for sort of how to design these interfaces in safe languages. There's a bunch of challenges in using an ownership type system for a system like this. And if you want to hear like a really a little bit PL-y, but like very good account of this. There's a paper by Dan Grossman from 2002 called Existential Types for Imperative Languages that like predicted all the problems that we're facing now. And there's of course details about the process model and stuff that I didn't talk about. There's a bunch of stuff that the operating system can't do. One notable one is that we have to trust capsules for liveness. Otherwise, we just can't enforce the invariance that we want to. Okay, and I don't have a ton of time, so you can read the summary. I talked about the stuff that I talked about. Thank you.
Any questions?
I heard Rust binaries are really big. What has been your experience with binary size on these microcontrollers?
So the 30 kilobytes of flash is a little bit of a lie. To get to 30 kilobytes of flash for the kernel binary, basically, we had to remove the definition of panic. So that seems to be the main source. That seems to be the main source of size for the binaries. Basically, lots of operations that could happen, like for example, unwrap in an option, could panic. And if you have the definition for panic, the binary will contain a bunch of formatted strings for panic to output. That takes up a ton of space. Like in our case, like I think it was twice the binary size without removing the definition for panic. In theory, that's like not necessarily useful, so you could remove it. It turns out to not be very user-friendly to remove right now. You have to like change libcore, which you ought not to do. But yeah, Haskell binaries are bigger.
This is great. I really love this. Question. You didn't really say what kind of, or like how small these microcontrollers are. Like, do you have privilege separation, memory management unit? So, where are these processes, magical processes coming from?
Yeah, so in order to do processes, we need some hardware mechanism. Basically, these are ARM Cortex-Ms, and the new variants of Cortex-Ms, as of like the last 3-4 years, have this mechanism called memory protection, which is unlike a memory manager in the sense that there's no virtualization, but basically, you get to set read-write execute bits on relatively small regions, as small as like 32 bytes up to the whole size of memory, but it's a flat memory address space.
You mentioned towards the beginning that that kind of the state of the world here is vendor-provided binary blobs for Bluetooth and Wi-Fi and these sorts of things. Are you completely precluded from using like vendor-provided drivers in this model?
So I didn't say binary blobs, although that is the state of the world for the most part. We cleverly avoid using hardware that requires us to do that. Basically, no, you can't use that. The only way to use binary blobs is typically if they're a driver, it might be a binary blob, but there's some like shim layer that you need to implement for your particular microcontroller. We can put a shim layer that talks over system calls to the kernel, so you can do things like what we do, like put the Bluetooth driver in a process, and that could be a binary blob, and then that talks over a system call interface. But like, no, we can't deal with binary blobs at all. Cool.
In your code example, you had a struct that had a borrowed vec of U8s. Where is it borrowing that from?
A borrowed?
Way back. You had in your like example, that one. Yeah. Where is it borrowing that?
The slice. Yeah, the slice. Yeah, I elided the lifetime annotations here. You should think of these as being tick static. In practice, there's but just for general, they're in practice tick static. The way it's implemented is there's like a lifetime argument that all the borrows have to use. Basically,
my question is exactly like, what is that buffer pointing to in memory?
Yeah. So generally speaking, some like static array that you've allocated when you initialized the capsule. So there's this is in the limitations I didn't go over. There's this like big, awful, very unsafe configuration file that the platform integrator has to write to basically cobble all these things together and statically allocate a bunch of buffers for each thing to use. Yeah.
What's the like the build tool chain like for this?
Ooh, well, did everyone hear the question? The question was what the build tool chain is. So there's a couple things that could mean, but I think like right now we have a bunch of terrible make files. We're also behind on Rust Nightly by like a year, I think. So, so the what? Oh, is it? Yeah. But other systems that do, like other operating systems in Rust successfully use cargo very nicely. That's what we hope to end up using. If that's what you meant, that's the answer. We have terrible make files that break all the time. But cargo seems to be able to solve all of our problems now.
In your research, have you thought at all about verification of programs? Because it seems like this would simplify that as well.
Yeah, not deeply, but I think so. There's this sort of big rush for doing software verification or like proving code correct. And you know, one way of looking at it is that the high bid is that it's possible, but a lot of effort. So to me, it seems like a really sort of fruitful, could be a really fruitful place to sort of, you know, tie these things together where like maybe there's sort of core components that are very difficult to do safely in the type system, but you could prove correct, maybe with a lot of effort, but they're like small, relatively unchanging, and like the rest of the safety semantics happen on top of that just with the type system. But that's all just like, I've thought that it would be cool if somebody did that. I don't know how easy it would be.
This is the last one. We need
Is this all open source?
Yeah, totally. I didn't put a link to the repo, which was stupid of me. It's on GitHub under the organization Helena-project. I really should have put a link up. I'm sorry.
There should be a link to the project on the
right.
Meetup page.
That's right. Thank you, my savior again.
All right. Cool. All right, well, thank you very much. All right, so next up we have Johannes. I hope I'm pronouncing that correctly on the internet. It will take a moment for us to switch over to him. Okay, we have slides.
Hi, can you hear me?
We can hear you. We don't see you yet. Okay, there you are.
That's weird.
Okay, great.
Oh, okay.
All right. Well, take it away from Amsterdam, I believe. Oh wait, no, don't take it away. Pull it back.
Okay. Can I start?
Yes, you can. All right.
Great.
Please give him a warm welcome. Hopefully.
Okay, so this is about bioinformatics and how to do that in Rust. So let me first introduce a bit of bioinformatics to you. So bioinformatics is a field of science that kind of combines computer science, statistics, and mathematics to interpret biological data. And it typically involves a lot of mathematical and statistical modeling, machine learning, and algorithm engineering, all kinds of stuff you can think about in these fields. And however, today, with the kind of data we have, almost always it has to deal also with biological sequences. So what are biological sequences? The most important sequence in biology is the DNA, which encodes the genome, which you can interpret as the blueprint of an organism, and it appears in cells in the form of chromosomes, like you see here on the left side. And if you look into these chromosomes, they are basically double helices of two complementary DNA molecules that are kind of glued together. And each of these DNA molecules is a chain of so-called nucleotides. And the nucleotide is a molecule made of phosphate sugar and a base. And these bases, you have 4 different bases, adenine, cytosine, guanine, and thymine. So as a computer scientist, you just assign letters to them, A, C, G, and T. And importantly, the sequence of these bases is the blueprint of the proteins that are appearing in your body. And so from the computer science perspective, DNA is just a text over the alphabet A, C, G, T. And the second important type of sequence are proteins. So I already mentioned proteins are generated from the DNA. So the DNA basically tells the body about the sequence of the protein. And again, a protein is also just a sequence, in this case not of nucleotides, but of amino acids. Amino acids are molecules made of carbon, hydrogen, oxygen, and nitrogen. Theoretically, there are about 500 known. However, in the body, only 20 are actually used. And the idea is that basically a sequence of 3 nucleotides from the DNA encode for 1 amino acid. And basically, the DNA gets kind of transferred out of the nucleus of a cell into the cell plasma, and there it basically serves kind of as a blueprint for encoding these amino acids, which are then generated into these chains here that fold into proteins. And then these proteins conduct all kinds of functions in your body, like being a catalyzer for reactions, chemical reactions, and so on. And so these 20 amino acids, again, make an alphabet for us over these letters here, and this is, again, a text we can deal with in bioinformatics. So in the end, you always kind of want to analyze these sequences, compare them against each other, and so on. And this is usually a big data problem. So, for example, the size of the human genome is about 3 billion bases, and a single sample that measures something in the human genome can range from 5 to 300 gigabyte of data. And example research questions you can ask about such a sample or a couple of samples is, for example, to find mutations in them, to investigate genes that are similar between species, identify species within the pooled sample, and so on. And the techniques we use typically come from pattern or string matching. We use succinct data structures and full text indexes, and so on. So let me talk a bit about Rust Bio. So bioinformatics software in general, there we have kind of a gap between what we want and what we have in reality, I would say. So as we have these big data, we surely want fast implementations. And since bioinformatics is more and more also involved in medicine, especially in personalized medicine, these implementations should be essentially bug-free, and we should really be able to rely on the results we get from that. However, in reality, it's actually like that the people who implement software in bioinformatics are mostly people with fixed-term contracts, like PhD students and postdocs, and they naturally have only very limited time. And that's why people usually tend to use scripting languages to achieve what they need. And then their contract ends, they move away, and then the program maybe stays there, which has been published in some kind of paper, but nobody maintains it anymore. It might contain a lot of bugs still. And so this is really a bad situation, which might be a general problem in science, but I observed this particularly in bioinformatics. So my idea was kind of to let the Rust compiler do the work that the people in bioinformatics sometimes can't do because they don't have enough time. So I already said that they have limited time, so it might be counterintuitive to say, okay, they should use a language and a compiler which is so strict and it's so much effort to get something to work. But on the other hand, my impression is actually that you just shift the development time from the time you use for debugging some kind of scripts to time using it for making it compile and making the compiler happy. And so my proposal is to just rely on the compiler, the linting system, and the ownership model to solve all the code quality and bug issues you usually have with bioinformatics software. and that we are really suffering of. And I think Rust can solve these problems. So let me come to RustBio itself. So RustBio is a library of bioinformatics algorithms and data structures that are very commonly used in all kinds of problems that occur in bioinformatics. So obviously pattern matching algorithms, an alphabet implementation, so-called pairwise alignments, all kinds of indexes, suffix arrays, Burrows-Wheeler transformations, Q-gram index data structures, rank select data structures, obviously also readers and writers for common file formats, and log space probability implementations. So let's become a bit more concrete. So I picked one example that might show some features of Rust we use, but also provide some typical example of what you do in bioinformatics. So a very common task in bioinformatics is to align sequences against each other. What this means is that you have given two sequences A and B, maybe over the DNA alphabet, and you want to find a combination of substitutions, deletions, and insertions in the one sequence that have a maximal score or alternatively a minimal cost, and transform, in this case, sequence B into sequence A. So if you look at the example above, we have a rather long sequence here, A, and a shorter sequence B. And a possible alignment of B against A would be that we first take the first three bases of A, then we have a deletion in this sequence here, and then we take again three bases, then we have a substitution here, and then we have matches again in the end. And this is a very common question in bioinformatics. For example, to find mutations and so on. And so technically, how do you do that? So there's a very well-known dynamic programming algorithm for sequence alignment. And the basic idea is that you take the two sequences you're interested in and you construct a graph out of that where the edges represent operations on the sequences. So diagonal edges would be matches or substitutions. And horizontal edges would be deletions, and vertical edges would be insertions to the left sequence here. And then each of the edges has coasts or scores, depending on how you define it. And an alignment is a path from the top left to the bottom right. And yeah, so an optimal alignment would obviously be an alignment which has either minimal coast or a maximal score. So that would be a path here. This path would be the optimal alignment here. And yeah, so there are a couple of variants of the sequence alignment problem. So obviously you can define arbitrary coasts for the edges or scores. Most prominently in bioinformatics are so-called affine gap coasts, where it's actually expensive to open a gap, like an insertion or deletion here, but to extend this, it's not that expensive. This comes from a biological intuition, actually. And then it might be, you might have different coasts, whether you substitute a T against a C or a G against a T and so on. And defining these coast functions should be quite variable. And second, there are different variants of alignments itself. So as I already mentioned, an alignment would be a path from top left to bottom right. That's also called a global alignment because it aligns the whole part of the sequence B against the sequence A. But there's also a so-called semi-global alignment where you just require a path from top to bottom. That would mean that you align all of sequence B, but in sequence A you might just omit certain parts at the beginning and the end. And then there is also a local alignment, which means that you just are interested in the top scoring path within that graph, but it does not necessarily need to reach the top left and the bottom right at all. Yeah, so these are the variants that we have. As I already mentioned, this can be implemented by dynamic programming, by obviously just looking at the last column you investigated and the current column, and then investigating the scores and determining the maximum score. And yeah, if you do that in the end, if you process the whole graph, but you didn't have to have it in the memory, you end up with the optimal alignment score. but you actually don't have an idea what is the actual alignment. And to get the actual alignment, you have to additionally store some kind of traceback that gives you the optimal decision you took in each column, basically. And you can do that quite space efficiently by using bit encoding. And yeah, so how is this available in Rust Bio? Let's look at a little example here. So we have two texts here defined at the top. Then we define a scoring function with a closure here for substitutions or equal basis. So in case of equal basis here, we just return 1 as a score, and for a substitution, we just return -1. Then we define gap open and gap extension codes, and finally we can initialize our aligner. In this case, with some hints about the length of the two sequences, and yeah, the scores that we defined above. And yeah, this aligner object can then be used to, for example, perform a semi-global alignment for the two sequences we have here at the top. And the resulting, the returned object can, for example, be used to pretty print the alignment, which you can see here. And we can also just access all the alignment operations that are done in the optimal alignment, and we can output something that's called a SIGA string, which is a condensed representation of the alignment using some kind of encoding here. And yeah, technically, this aligner object is just a struct here, which allocates certain dynamic programming matrices, only consisting of the last two columns here, traceback matrices, and the scores. And the idea about using this aligner object actually is, or struct actually is, that you can reuse the allocated memory for the dynamic programming and the traceback for multiple alignments, because it's very common that you don't do a single alignment, but rather hundreds to thousands or even millions of alignments of mostly sequences of the same size, and thereby we just can reuse the aligner without reallocating all these matrices. And the second technically interesting part of the alignment is how the actual dynamic programming algorithm is implemented. So as I already said, there are different variants like global alignment, semi-global alignment, local alignment, depending on where your path shall be located in this graph. And however, the dynamic programming algorithms look very similar. And therefore, I decided to kind of make use of the Rust macro system to avoid code duplication. So I don't go into all the details here, but basically, you see in this line here the outer loop, which iterates over the columns, and then you have an inner loop, which iterates over the rows of each column. And what's in here is actually the real dynamic programming, where you access the previous column and calculate the optimal scores of your current column and so on. And then you have the macro allows certain blocks here. So for example, there's an initialization block that appears before each column is processed. Then there's an inner block which appears within each row of a column. And then there's an outer block that appears after one column has been processed. And these three blocks can basically be used to encode any kind of alignment we want to have. So the first case is the global alignment. In that case, we just need to use the init block and initialize the dynamic programming matrices in a certain way, and also the traceback matrix. And the inner block and the outer block can essentially be empty here. And for the semi-global alignment, we just use the outer block. So yeah, we also use the init block for a small statement, and we use the outer block to decide after each column has been processed whether basically which cell in that column contains the optimal score so far. And finally, for the local alignment, we have to decide basically for each row in a column whether we already have an optimal path, and then store the address of that path, basically. And yeah, so this is the alignment module of Rust Bio. Next, I want to just show some general purpose data structures that are also available in RustBio and that are very often used in bioinformatics. The first is bit encoding. As I already mentioned, we need that basically to encode the traceback matrices in the alignment. So the idea is that you sometimes want to store integers in kind of a vector, but these integers don't use the full 8 bytes you at least would need for that. And therefore, you can encode them, for example, with 2 bits instead, which is allowed by the bit encoding data structure in RustBio. So you just initialize it with the number of bits used for encoding, and then you can push values which would panic if a value exceeds the available bits for encoding it. You can have random access, and you can also iterate over the values here. And this is just implemented by a vector of bytes, and then we just encode to whatever is provided in the constructor of the object here. And the second data structure I want to mention is a small integer data structure. So the idea is that you, at least in bioinformatics, but I guess it's also a common problem in other fields, you sometimes have like vectors of millions of integers, and among these, most of them are actually very small. You could maybe encode them in a byte, but some of them are bigger, and you just don't want to waste the space for all of the integers just because some of them are bigger. And therefore, we offer the small inst data structure, which you can parameterize with the types for the small integer and for the big integers here. So in this case, it's a byte for small and U64 for big integers. And then it allows just to push values, either small ones or big ones. It allows random access and iteration, and obviously it won't store all of them in the same data structure. So how is that implemented? So the idea is that we have a struct here with a vector for the small integers and a B-tree map for the big integers. And so basically the B-tree map assigns indexes of the small ints array to big integers that are stored in there. And the small ints array just contains all the small integers, and we encode the case that we have an integer that is too big for the small ints integer array by storing just the maximum value of that type that we defined here, the type S. And so whenever we query that and hit a value that is the maximum of the type S, we have to look up in the B-tree map where the actual big integer is stored here. And by that, you can save a lot of space and basically compress your data structure. And so the last thing I want to mention is a rank select data structure. So I guess many of you might know that, but I still want to briefly introduce it. So rank select are operations on bit vectors. So this is a bit vector here. You have 2 bits of value 1 and the rest is 0. Then the rank of that would be what you see here. So basically the rank is the number of 1 bits that occur up to the current position. So in this case, we have 0, 1 bits occurring in the first 4 positions. Then we have a 1 bit here. So the rank of this position is 1. And then following that, all the elements here have rank 1 as well, until we have the second 1 bit here. So the rank increases to 2. And so on. So this is kind of an important data structure where you want to look up indexes of bits actually in an auxiliary data structure, for example. And so in RustBio, this is implemented using the bitvec create. So basically, we first create a bit vector, set some bits, and then we can initialize the rank select data structure from RustBio with a number of bits and a sampling factor, basically. And this sampling factor is used to divide this bit vector into so-called superblocks. And we actually only store the ranks for the superblocks, and we interpolate the ranks for bits in between these superblocks by using population counts. And this allows us to query the rank and the inverse operation, the select, where we just want to see the first index with a given rank in a meaningful complexity, in reasonable complexity. So basically, this is a so-called succinct data structure. So we just use linear space for the bit vector and sublinear space for storing the ranks instead of just actually storing each of the ranks. And this is very space efficient then. And by selecting the size of the superblocks here, we can basically adjust the trade-off between space and time complexity for the queries, actually. Yeah, so finally, some outlook, what we want to do in RustBio in terms of Rust itself or the Rust implementation. First of all, we right now use type aliases to the standard library wherever possible. So for example, texts in RustBio are just byte slices or the corresponding iterators. In the future, we want to look into using new types where the distinction makes sense. So for example, we have an implementation of suffix arrays, which are essentially vectors of integers. But of course, you can imagine if you take such a suffix array, which gives you some information about your text, basically the sorting of the suffixes of the text, and you just modify it, it's not actually a suffix array anymore, and we want to use new types to encode this behavior, basically. And as I mentioned, we have a log space probability implementation, and we might use new types for that as well, and all kinds of other data structures where new types make sense, actually. Yeah, second thing we want to look into is parallelization. So right now we just care about it in terms of implementing send and sync wherever needed. In the future, we might look into using something like Rayon to implement divide and conquer parallelism where it's possible, and let the user decide about the thread pool size via using modifying a global switch, basically, how it's implemented in Rayon. And this might give some additional flexibility in terms of parallelization. Yeah, so finally, I want to thank all the contributors, most importantly, Adam Perry and Taylor Kramer, which have recently been doing a lot of work in RustBio. And I want to also thank the authors of these very useful crates we make use of in RustBio, most importantly, ITATools and CSV, but also NAlgebra, Aprox, and Serde. Yeah, thank you very much.
Questions?
Hello?
Hey. Okay. Oh, yes, Cameron.
Why did you end up using macros instead of a trait for the different dynamic programming loops? Could you say a little more about the trade-off there?
Yeah, so actually, I didn't benchmark it. So at the time I implemented it, I just was excited about these macros, obviously. But so I would see, so we really have this thing in the inner loop, and there we would have an additional function invocation in case of using a trait. And I just thought it might be a additional performance benefit, actually. It's not that complicated, the macro, so I just tried it out and it worked out nicely. So it's just like getting rid of additional function invocations, essentially, because these alignments are quadratic complexity, and we have cases where we really have a lot of them over very big sequences, and there each operation actually matters. So it's just optimizing.
Great. Any other questions? Well, thank you very much. That was really neat.
Thank you.
All right. And that brings us to the close of another meetup. If anyone ever wants to give any talks, please come talk to me or mail community team at rustlang.org or whatever. And I will hopefully see you on August 13th. So have a good night, everybody. Goodbye.
Bye-bye.
And we